In today's lecture, we're going to talk about streaming, and many of you have already been introduced to streaming in our project discussions. Some of you have presented problems based on streaming, so I presume this is not very new to you, so largely going to jump right into the topic, but I thought I'll talk a little bit about the first time I came to know about streaming. This was several years ago. To be precise, it was actually SOTA 2003. And this notion of streaming, the topic of streaming, was introduced by the plenary speaker of SOTA 2003, who was Muthukrishnan, pictured here. A very interesting personality. I believe I haven't really met him face to face, but I've seen him several times. Excellent speaker. And one characteristic about him is every time I see him, he has a different hairstyle, a different hair color. So anyway, this is how he introduced streaming. You are standing, on a stream or by a stream, and you see different types of fish go by. And he introduced the notion of streaming as you see all these fish going by, and you have some questions in your mind about the fish, but unfortunately you cannot catch and store all the fish, so you have to let the fish go by, and then you, at the end of the day, after a long day of fishing, you have some questions about the type of fish that you saw, the biggest fish, the smallest fish, the average size, and that's just to get us started, and then many such questions. And so this is the kind of colorful perspective with which I was introduced to streaming. So without further ado, let's get started. Let me introduce the streaming model. So the data flows as a stream, and you get to see data one item at a time. And here you are looking at the data, and each time you get to see one data item. And let's give ourselves some notation. So let's say the data item started from A1, A2. You're currently looking at AI, and so on. And the data stream keeps coming in at every time step. And you don't get to store the entire data. At each point in time, you can do some temporary computation, which we don't really care about how much computation we do. But the essential thing we do is that we have some sort of a synopsis or a sketch that we maintain. Okay? And typically this synopsis or sketch is going to be much smaller than the size of the stream. So we don't assume that we know the size of the stream. So this quantity is an unknown. And however, the synopsis itself is assumed to be very small, and typically little o of n, often as small as O of log n, O of square root of n. And in fact, we're going to see one example where we only use O of log n space. So with this, let's jump into a problem. Let's say that we are getting a steady stream of items, and we don't even know how many items there are in the stream, but we want to count the number of items. And this is of course quite easy, because all we need is a counter of O of log n bits. And in fact, with a counter of O of log n bits, we can count n accurately. The challenge is think of a situation where the number n is very large, and you want to count using very few number of bits. And this could happen in cases like embedded systems that see a lot of data, but their design is they're designed to be working with such resource constraint context that memory is at a premium. Um, and so in situations like this, it it's interesting that we can actually get a rough estimate of the number of items with far fewer number of bits. In fact, what we're going to see now is a way to estimate n within uh, an epsilon fraction. So in other words, we're going to get an estimate n hat that's going to belong to n minus epsilon n and n plus epsilon n. We're going to be able to give this guarantee with probability at least 1 minus delta. And such an approximation is called an epsilon delta approximation. And believe it or not, this problem was actually studied way back in the 70s, and in some sense, it's not very surprising because memory was a lot more expensive back then, and so it was important to design algorithms of this nature even back then. But I don't think the author realized how important and fundamental these ideas are going to be, and how they're going to lead to very interesting work starting from the late 90s and 2000s and onward. So this the algorithm that we're going to study was introduced by Morris, and later it was analyzed by Fliolet in the mid 80s. So here's how this algorithm goes. We initialize a variable x to 0, and each time we see a data item, we update x with some probability. So in particular, whenever we see a new item, uh, we flip a biased coin, and with bias 2 to the minus x. And remember, x is a value that's going to be incremented over time. If this biased coin comes up with a heads, then that's going to happen with probability 2 to the minus x. Then we increment this quantity x. At the end of the stream, when we come to the very end of the stream, and now we need to know how many items we've seen, we simply output 2 to the x minus 1. And why is this even correct? I mean, what is the intuition behind this algorithm, you may wonder. So what's going on is the following. We start off with x equal to 0. First time we see an item, our x is going to be a 1. And then subsequently, with probability half, roughly speaking, you are going to increment in the next couple of occasions. So that would lead us to, so this is items 1, 2, 3, 4, 8. Now as you can see, when we see the second and third item with probability half, intuitively speaking, we would increment. So by the time we come to 4, we would have probably reached x value would have reached 2. Between 4 up to 7, you would be incrementing with probability 2 raised to the minus 2, so with 1/4 probability. So between this range, you expect to increment by 1. And then between 8 and 15, you again hope to increment by 1. And from 16 to 31, you will increment by 1 on expectation, and so on and so forth. So every time the numbers double, you increment once. The rate at which we increment is logarithmic, and the number of bits we need to store the counter is only log of log n. So that's the intuition, but let's look at it a little bit more carefully and more formally. So the claim we would like to prove is that the expectation of the random variable 2 to the x is n plus 1. and this is why we output not 2 to the x but 2 to the x minus 1. So we output n. So the question is, why is this claim true? So let xn be the value of x after seeing item n. So now the expectation of 2 to the x can be written in this way. It's the summation of I going from 1 to infinity, probability that x n minus 1 equal to I, times now given that x n minus 1 equal to I, you want the expectation of 2 to the x n. So in case you are wondering where this comes from, you can refer to Mitzenmacher and Upfall, page number 27. That'll be a good reference for you to verify this formula. Okay, so now we have the summation of the overall I, the probabilities of xn minus 1 times, and now we need to expand out the expectation, this conditional expectation that we have here. Of course, this 2 to the xn, remember, we're conditioning on xn minus 1 equal to I. And if you know that xn minus 1 equal to I, then from the algorithm, we know that we're going to increment with probability 2 to the minus I and stay the same with probability 1 minus 2 to the minus I, which is exactly what is given here in this formula. So with one, or I'm getting my i's and j's mixed up, so let's call this i's. Okay. So with probability 1 over 2 to the I, we have we're going to increment. So 2 to the xn will become 2 to the I plus 1. And with the remaining probability, it will stay 2 to the I. Okay, so let's expand this out. And with a few cancellations, we're going to get the summation of the probabilities times 1 plus 2 raised to the I. When we take the summation inside the parentheses, now this is going to be two summations. The first summation is just going to be 1 because it's summation over all possible probabilities of a probability space, and the other summation of this one, let's look at this a bit carefully. So this is going to be nothing but the expectation of 2 to the xn minus 1. Okay, so this is nothing but 1 plus the expectation of 2 to the xn minus 1. And so now what we have is some recurrence that we can expand out. So it's going to become 1 plus e to the 2. And this can be expanded out, and we will finally get n minus 1 plus the expectation of 2 to the x1. But x1 is always 1, and therefore the expectation of 2 to the 1 is going to be just 2, and that's going to evaluate to n plus 1, which is exactly what we wanted. So here's a quick exercise for you. This is just to give you some context. This exercise is designed to move us towards an understanding of the variance of this random variable x. We want to show that the expectation of 2 to the 2x, which is essentially the expectation of 2 to the x squared, um, goes up to theta of n squared. And so you can show this using the same technique that we used to show the expectation of 2 to the x. And the implication of this exercise is that the variance of 2 to the x is equal to theta of n squared. And when the variance is theta of n squared, the standard deviation is of the order of n. And if you work out the math, this is not going to be a reasonable approach to get a good epsilon delta approximation. So we need to be a bit more careful here. So this is a good starting point, but in order to get a good epsilon delta approximation, what we're going to do is not just have one estimate, but several estimates, and then take the average. And we'll see that by doing that, we can bring down the standard deviation of the estimate to a point where we get the appropriate epsilon delta approximation. So I'm going to call this algorithm Morris plus plus because it's one step. It's a one-step improvement over the classic Morris algorithm. In this, we have a parameter t, and that's parameter is going to be of theta of 1 over epsilon squared delta. The exact constants can be worked out in the analysis. So here's how we're going to do this. So we're going to maintain t variables. We're going to call them x1, x2, and so on up to xt, and we're going to initialize all of them to 0. So this is essentially implementing Morris's algorithm in parallel. As each item arrives, we execute the following line in parallel for each value of I ranging from 1 to t. And we do this independently. So when for any given value of I with probability 2 raised to the minus xi, so it only uses the random the variable xi with probability 2 to the minus xi, we increment xi. So these are the variables x1, x2 up to xt are manipulated completely independent of each other. Okay, but at the end, when the stream ends, we simply output the average of the estimates. So when the stream ends, we simply return 1 plus the average of 2 to the xi. So let's analyze this Morris plus plus algorithm. Let's use Z to denote the average value of 2 to the xi's, which is essentially 1 over t summation 1 to t 2 to the xi. So the first question is, what is the expectation of this z? Well, the expectation of each of the 2 to the xi we know is n plus 1, and you sum them up and divide by t, so that's essentially going to be n plus 1. So there's no change there. So we're still going to get a good estimate, well, with the correct expectation, but hopefully the standard deviation is improved. So let's see how we can show that. So for that, we'll have to look at the variance of z. So we first simply expand out z. So this is what shows up here. Now, of course, we can bring the t outside the variance, and that gets squared when we bring out a constant term outside of the of variance. And moreover, the variance of each of the 2 to the xi's is is equal to each other, and so this is the summation is really summation over equal variance terms. So that and it's summed from I equal to 1 to t, so that t can be brought out as well. So it becomes 1 by t variance of 2 to the x. And of course, we know that the variance of 2 to the x is some theta of n squared. You should have worked it out as an exercise. So if that is the case, then this variance becomes theta of n squared divided by t. So as we increase t, we can get better variance. So now, assuming n is sufficiently large, look at the probability that this random variable z is far away from n. So in particular, z minus n minus 1. Remember, the expectation of z is equal to n plus 1. So the probability that z minus the expectation of z is greater than epsilon n is at most the variance of z over epsilon square n squared. And of course, this comes by Chebyshev's inequality. So applying our knowledge of the variance of z, we get theta of n squared over t times 1 over epsilon square n squared. So now the question is, we know that t is theta of 1 over epsilon squared delta for suitable constants. So if we substitute that, some of the terms are going to get cancelled out, and this probability can be brought down to delta for a suitable choice of constants. So just to conclude this, each execution of the Morris algorithm will require log n bits, but we repeat it t times, where t is theta of 1 over epsilon squared delta. So our total memory is theta of log n divided by epsilon squared delta. So now here's an exercise for you. Extend this Morris algorithm in order to achieve a memory requirement of only log 1 over delta times log n divided by epsilon squared. So essentially instead of a 1 over delta term, we're going to have a log 1 over delta. So that's a pretty significant improvement. As a hint, please note that you will have to use the Chernoff bound to achieve this this bound.